Welcome everyone to our my talk on transition to digital engineering, case studies and concepts. This is put together by myself as well as Professor Ann Batchelor. You mostly have me today giving the talk, but this is kind of an update. You'll see lots of content from a similar talk we gave last year, but there's been some updates to this very relevant topic of digital engineering, the transition to it. So the goal here is to define the terms, the concepts, give some examples, motivating reasons why you should be considering this as a part of your organization, as a part of the research you're doing, et cetera, and how it connects in particular to systems engineering. So we'll have a very brief introduction / motivation. I'll go through a number of kind of definitions to hopefully maybe get straight in your mind what's the difference between digital transformation and digital threads and digital engineering and model-based system engineering, all these different terms. I'll try to give you some more concrete definitions and kind of what they imply and how they're related. We'll have a couple of case studies that motivate kind of some of the benefits, give some evidence to the benefits that we put forth in terms of applying digital engineering to a variety of different complex system development projects. I'll have some comments and tips, and then finally, I hope we have some time for discussion. So some high-level discussion questions for those both in person and online to understand your opinions on digital engineering, where you've seen it work and not work, those type of things. All right, so introduction. So this motivation will be primarily, at least initially, Department of Defense focused, because there's a lot of really good drivers in that space in particular, but a lot of these points can be made for public-private sector more broadly in the organizations that are developing complex systems or have to do better job of their system development processes to meet the challenges of today's environment. So let's talk about system engineering in general. It evolved in about 40s through 60s as kind of as a discipline, right? That's a fairly long time ago at this point. When the first iteration of the Defense Acquisition System standard was published, it was in the early 70s. If we think about how much the world has changed since then, there is little to no software engineering, manufacturing automation, the World Wide Web, virtualization, model-based systems engineering, Industry 4.0, digital twins, the definition of that, all of that, there's very little of that at that point in time. So a lot of systems engineering practice came from a point where we didn't have a lot of these tools and features available to do our engineering activities. So throughout all this change, the mainstay of systems engineering and the associated DoD acquisition guidance has continued to center around physical realization of large-scale monolithic systems intended to persist for many years. That's kind of the type of system that a lot of the system engineering practices are built along. However, recent National Defense Magazine article points out the problems with maintaining technological superiority when we are encumbered by rules of the U.S. acquisition system and efforts. We need to rethink efforts taking place to transform systems engineering, also engineering more broadly, as well as the whole organization in of itself, if we want to maintain our technological superiority, develop products more efficiently. Well, there's a lot of factors here that are driving this kind of digital transformation. So furthermore, factors like cost optimization and affordability is increasingly important to maintain competitiveness. So how do we do this? Can we continue our existing practices, or do we need to, understand and use techniques that are kind of this digital engineering envelope to today's needs? So as I mentioned, there's been a push and changes, especially in kind of the DoD space, with the insights in mind of I need solutions to come more rapidly to meet today's needs. So in 2021, DoD published the latest 5000 series guidance, the adaptive acquisition framework, which recognizes new development and acquisition pathways, and in particular ones that are much faster, much more rapid in their development timelines and scales. We see things now on the order of less than a year. There's still things longer timeframes as well, but if we're trying to meet these goals for different types of systems, we need to be able to identify methods that will allow us to do the correct development of these systems within the target goals. And one of the areas they specifically identified was digital engineering as a way to meet these needs. So, continuing on this mindset, how are things changing? Well, things are becoming more complex. One measure of this might be the lines of code. As I mentioned earlier, right? Older systems didn't have a lot of code on them. Modern systems do. And here's an example of some different areas, manned spacecraft, unmanned spacecraft, commercial aircraft, military aircraft, where we kind of see exponential trends in the increase in the number of lines of code that are going to be put on or developed for these different systems. And the ability to manage systems with this level of complexity becomes more and more challenging if you kind of use perhaps more traditional engineering and systems engineering approaches. Furthermore, there's kind of this idea that to emphasize how would a modernized life cycle for systems engineering look? And a lot of experts are putting forth it needs to be more agile, more data, more model-centric to meet the needs of the modern era. And here's one visual representation of this concept. This is representing a circle, something that is a little different than classical system engineering understandings, where we would want this more circular definition of how both the system of development evolves as well as the system is maintained over time. And this layering is key to this perspective here. We see kind of in the outer layers, we're looking at more of the learning, building, and measuring for our system development processes. But how can we achieve this in the terms of kind of this more agile perspective and one that supports a cyclic nature of modern systems engineering? Well, we have models and we have data at the center, the mechanism that helps connect these different layers together, having different types of models, different types of ways to connect the data, the concepts we're going to define in the next section in particular. Okay, so that was some brief motivation. So now I want to kind of get into some of the terms and definitions and the concepts here. So we'll talk about digital engineering, then digital twins, digital threads, model-based system engineering, and then digital transformation with some kind of discussion of each one of those points. So digital engineering. Digital engineering is defined as an integrated digital approach that uses authoritative sources of systems, data, and models as a continuum across disciplines to support lifecycle activities from concept to disposal. So, let's break down this definition a little bit and understand an effective digital engineering strategy aims to do a few different things. It seeks to formalize the development, integration, and use of models to inform enterprise and program decision-making. It seeks to provide an enduring and authoritative source of truth so that stakeholders can have current, authoritative, and consistent information for use over the life cycle. If we think of that kind of circular image we saw a few pieces back, by having a single thing at the center, a more data and model-centric element at the center, that can be something that continues as cycles repeat to be the single source of truth, the authoritative source of truth that continuously gives us a place to understand and develop the system rather than disparate, perhaps unlinked approaches that are sometimes used. It also aims to incorporate technological innovation to improve the engineering practice beyond traditional model-based approaches with rapid implementation of innovation. So I'll give some examples of some of those innovations, but there's ChatGPT and all that discussion along that side, and how do we bring that into, for example, the engineering process? Well, having a more digitally focused approach to doing engineering allows you to better integrate in new technologies to take advantage of these approaches, as well as provide mechanisms for this approach to integrate into your existing processes as well. This also seeks to establish supporting infrastructure environments to perform activities, collaborate, and communicate across stakeholders. A big aspect of this can be communication. We might be still doing very similar activities in many ways. The outcomes are very similar. We're still making requirements, we're still building the products, etc. But what if we're able to communicate those different aims and goals, and then potentially 1,000-person teams can better communicate between their different respective domains? That's one of the aspects, one of the principles that we're seeking to enhance through more digital engineering focused approaches. And then kind of towards this, a more fundamental shift in transforming culture and workforce to adopt and support digital engineering across the life cycle. This might require more than just tools, more than just learning how to do it, but rather how can I adapt the organization and my own mindset in doing engineering when I have these new tools available. Okay, so related to this concept is the idea of a digital twin. So again, I'm going to kind of give a definition from literature for each one of these. Digital twin is defined as a set of virtual information constructs that mimics the structure, context, and behavior of an individual or unique physical. I think I have an echo. Oh, okay. Or a group of physical assets. Key aspect here is a physical asset that I'll mention in a second. Now, this is meant to be dynamically updated with data from its physical twin throughout its life cycle and informs the decisions that realize value. Now, I know that's a wordy definition, so there's also this working group that put forth this definition has a slightly simplified one. A digital twin is a virtual representation of a connected physical asset. And there's a couple of key aspects here to keep in mind. The essential elements of the digital twin are the virtual representation. We often call this some type of model of the asset. Another key aspect is a physical realization. So some sort of physical thing that we are trying to virtually represent with the digital twin. And the final thing, an important thing that sometimes is, I think, overlooked in this definition, it's not just having a virtual representation and a physical representation, having them conceptually linked, but no, we have a formal way to transfer data and information between the two. They are connected in some way, and we'll use the word digital thread in a second to kind of define that type of connection here. So digital twin encompasses the entire product lifecycle of a physical asset, sometimes called as designed, the design and engineering phase, the manufacturing phase as built, as well as the operational sustainment phase as used, as maintained. This idea that we have a virtual representation of the physical thing. And sometimes we might be building that virtual representation before the physical asset exists, but to have a true digital twin, we want that physical asset that we are comparing and benchmarking and connecting to between this asset and model. Now, why we want to do this? Well, one key aspect of having a virtual representation or model of our physical asset is the ability to do rapid exploration and understanding of our system. We might be able to try what if scenarios more effectively and at a lower cost, at a lower risk level by having a model representation of our physical system. We might be able to identify errors more quickly through this virtual representation. We might be able to communicate what the system is and how it's supposed to operate more clearly with the virtual representation than giving something the physical thing and saying, good luck making it work. There's lots of value that a digital twin might bring. Okay, so we talked about the connection angle here in the concept digital twin. Well, this leads to kind of the digital thread argument that we want to make. So digital thread is defined as a data-driven architecture that links together information generated across the product lifecycle and is envisioned to be the primary or authoritative data and communication platform for a company's products at any instance in time. So this really boils down to the idea of some formal communication framework that connects the traditionally siloed elements. I might have group A, group B, are they communicating? Are they talking together? That might be considered siloed if there's only a few meetings per year where they kind of talk and figure out issues. So by having a formal communication network linking these groups, you provide full traceability and connectivity throughout the entire life cycle, from concept to design, manufacturing, and service. So this end-to-end process visibility is required for better cross-team collaboration and early detection of anomalies to reduce these risks in particular. And one of the case studies will highlight this point where, by creating digital threads between the different aspects of the development process, information allows us to fix things earlier. That can be really beneficial, especially as it's typically more expensive the later in the development process that we identify those errors and have to correct them. So, connecting some of these ideas now, digital thread is the key enabler for realizing a true digital twin. We have that formal connection, a digital thread between that model and physical asset. But we'll have a visualization a little bit on this, but digital threads is not only between the digital twin concept, but also between other aspects that you may be using in your system development side. You might be doing things in requirements perspectives, in the software perspective, in the integration and testing side. You can build digital threads between those different kind of traditional perspectives that may often be relatively siloed through the digital thread kind of idea. So another point I want to emphasize here is that this is not putting forth the idea that there should be one common software platform. That's not really the goal of a digital thread. Rather, you still want to use the best of breed tools and data and couple them together through digital threads. So understanding how to do that is part of the digital transformation challenges that we may have, but it is not putting forth that you just pick one tool and do everything in that space. So let me give a kind of a visualization example here. So this is adapted from the reference above, showing there's lots of different activities you may want to be doing during our development of systems, requirements, system architecture, going to the top, hardware, manufacturing, quality assessment, software and testing, and DevOps at the bottom. And we generally would like to know, the purposes of these different activities is to be building a single system, not just the requirements thing and just the system architecture and just software, right? They're meant to be connected, at least informally. There's often information being passed through word of mouth or through documents, things like that. But the digital thread concept, represented here by these kind of arrows and orange lines, is that we want a formal way to link the tools and the data that's generated by those tools so that requirements can communicate and be reflective of system architecture and vice versa. Software and system architecture might be connected. Software and testing and DevOps and testing, all of those might be connected in some specific way through the specific tools and data that you want to use for those specific domains. So listing a bunch of tools here just to kind of emphasize the digital thread concept is connecting different tools or connecting different the data created from those tools so that information is updated from the digital thread. So there are many different tools for specific aspects of digital engineering needs. A bunch are listed there. Another point here is that this often requires training and the right mindset for effective use in a digital engineering environment. If you do have access now, to information from other areas, the data is available. Well, one basic thing is maybe you don't have to worry about creating that in your own tool. There often is duplication of work because you're simply trying to bring that information from one context into another. That's no longer required. But even, thinking more of like novel capabilities, digital thread will enable you to look further than where you were able to look before. It might have been too cumbersome to ask the questions of why was this done this way. If you weren't the one involved in it, you're now able to understand that better and perhaps reflect that in your own decisions during the system development process. And now a key aspect here is interoperability. Many large tool vendors in particular are building interoperability between their tools. And this idea of interoperability is an enabler of creation of digital threads between different kinds of tools and data. But there's also the idea of standards and formats, and this is often the mechanism being used to create this interoperability. Things like SysML or RecIF, Medelica, FMI, XML schemes, CSV, the OSLC, all these different standards. A lot of their goals is to support the creation of a standardized way to communicate between the different tools, which will enable digital threads to be created more readily, rather than having to make custom solutions for each individual interaction that you may want. Okay, so continuing now on our kind of definition train, let's talk about model-based system engineering, as this is a key aspect that comes up in the context of digital engineering. It's related to, but different, and especially kind of thinking of the system engineering perspective in particular here in this talk. Well, model-based systems engineering is defined as the formalized application of modeling to support system requirements, design analysis, V&V activities, beginning in the conceptual design phase and continuing throughout development and the later lifecycle phases. So the key aspect here is the modeling to support a bunch of things. So MBSE puts models at the center of system design and management rather than separate documents and pieces of data. Because of this, it can provide a critical single source of truth, a single point of access and definition for data or systems understanding. Now, you're kind of looking at the terms used here and thinking back to our goals and aims of digital engineering. These are very much aligned with the aims of digital engineering. So MBSE, the goals of like single source of authoritative truth, MBSE is a mechanism to enable that, to have something that can be the center of development, that can be the center of of communication. If you were paying attention to the last slide, for example, we saw like the system architecture side, which is often kind of in the context of MBSE, is kind of the key link between requirements, hardware, software, and their own individual branches. Now, MBSE, or really the model created with it, is often seen as a critical component of an effective digital engineering strategy and a piece of both digital threads and digital twins. So again, the ideas and the methods associated with MBSE kind of are very much aligned and therefore do normally fit within how we propose to do digital engineering in a practical way. Now, just to visualize this in case, again, you're not as familiar with these concepts, this emphasis on model versus document-centric. And this hopefully will kind of give you a perspective on why we might want to have more model-centric approaches in a more digital engineering environment. So more traditional document-centric SE approach might look like the following. Have lots of different groups, not just the engineering side, but also marketing and project management, manufacturing, analysis, engineering, a bunch of different groups. They're creating things that are used throughout the organization to communicate, is this going to work? What's our marketing strategy? What's the budget and project management goals, all that type of stuff. Traditionally, that might be done, individually in the groups, and they might be referencing, or what we have here is kind of implicit dependencies between documents, right? They're referring to other things, the analysis and engineering side and CAD side are all referring to the same objects, but they are not formally linking their understanding of them, their definition of them, the creation of artifacts for system, etc. Now, in a more model-centric approach, we put a system model at the center, where instead of having their own individual artifacts that are serving the purpose of communication and creation and development of the system solution and understanding of the system, we put a system model, a single or a relatively interconnected set of data objects at the center, where the different groups interface through this single source of truth rather than through multiple documents that have less formal dependencies between them. So this is more of a model-centric SE approach, where we put the model at the center of the different groups' goals and activities that they are looking to achieve. All right, so digital transformation is the final definition I have here. Digital transformation is defined as the integration of digital technology into all areas of business, fundamentally changing how you operate and deliver value to customers. So you can see, is engineering mentioned in this definition? It's not quite. So digital engineering might be seen as a part of a greater organizational digital transformation efforts. We saw on the previous slide, and engineering was one of those domains, but there's lots of other domains that might benefit from the model-centric, more data-driven approaches. And I would argue that that's more towards a digital transformation of the whole enterprise rather than just focusing on digital engineering as a subset of it. So one thing just to be thinking about is sometimes this might mean walking away from long-standing business processes that companies have built in favor of relatively new practices that are still being continuously defined. But as we talked about on the early motivation side of things, doing things the way that we are just might simply not achieve our goals. We might not make the products in the time we needed or within the budgets or deliver the capabilities that we may need to have. So a lot of the motivation here is we need something new to achieve our goals. The fundamental concepts in solutions put forth in kind of digital transformation, digital engineering are towards meeting those goals. Okay, so actually added one more quick example, but we have three short examples to kind of highlight some existing systems or currently being developed systems that have utilized the principles in digital engineering as well as MBSE and have measured or in some ways quantified the benefits that taking this more model digital approach added to the program. So let's go into those examples. So this first one is an airplane example. So Boeing received a large contract to build a number of advanced trainer aircraft, and the simulators for them as well. Here's a picture of it. So this T-7A Red Hawk is a supersonic plane, purpose-built with some certain kind of relatively novel things in mind for aircraft in terms of growth, improved supportability, and to innovate a maintenance-friendly design. So if I'm adding these new capabilities, how can I do that effectively? How can I, change, the fundamental paradigm that I might be, envisioning an aircraft to have? Well, they broke the norm by doing a bunch of different things. So first thing, the one that we're talking about a lot today, is digital engineering processes. They really embraced more of a digital engineering approach to the system development. They also did things like agile software development. They kind of thought about how do I actually create a solution that meets some of those, the ability to be supportable and maintainable. So principles like open system mission architectures, and that allowed them to do more rapid, affordable future aircraft development. Fully designed using 3D model-based definition and data systems as well. More generally, a more modular design was put forth, and it still achieved advanced fighter-like performance in these kind of training aircraft, one of the key capabilities that was desired. So the result of embracing, not just digital engineering, but more broadly, these other kind of more cutting-edge approaches to system development resulted from a much shorter concept to the first flight time of only 36 months here. Now, we can quantify some other things. So according to Boeing, compared to a more traditional aircraft development program, this particular program experienced a 75% increase in the first-time engineering quality, fewer errors, things like that, an 80% reduction in assembly hours, as well as a 50% reduction in software development and verification time. Those are very, we're able to produce the thing faster with fewer errors. Assembly hours might directly correspond right to the costs associated with the program, those type of ideas. So the benefits can be pretty compelling once the organization is able to transition effectively into a more digital paradigm. Another example here is on a submarine warfare federated tactical systems, kind of a system-to-system product with a lot of complexity in what it's envisioned to be. So, part of the motivation here is there's annual baseline updates that are needed that require processing thousands of baseline change requests and coordinating and verifying their implementation. Many different contractors, many different groups working on this, and there's many variations as well. The complexity of this effort, involves over 10 million source lines of code. I need to update that previous chart because this point's not on there, but it would be all the way at the top. As I said, the systems get more and more complex from the software side, but also from the cost perspective, the commercial off-the-shelf side, as well as unique military hardware. So how do you, bring those together into a validated system, and 10 variants. So we're not just developing one option; we're developing multiple options that need to achieve their specific capability goals. So in this study, MBSE rather than a document-centric approach resulted in lower requirements development costs and fewer defects that were also identified earlier in the process, which again has cost implications. So I'm showing you here kind of the systems engineering V, and there's a highlighting of where in this systems development process advantages were quantified and found. So for example, in requirements engineering, it was found to be 18% cheaper to do that particular stage. They also found that 8 or 9% fewer defects were introduced during the SC phases. And on the right-hand side, going up the right-hand side of the V, defects were found earlier. And, kind of, if we think of the propagation of the defects throughout the system and when they're identified, it's probably very hard to see, but these little red numbers are indicating the costs relative to, development versus when you're trying to do integration and tests and other things. So 1x, 5, 20, 80, 300 to 1,000x. So the earlier you're able to identify these errors, the less time, the less cost will be required to fix them. So that was also quantified for this particular program. So the more effective, more model-centric digital engineering approach was shown. So these are all good numbers, but one aspect to be thinking about here is there's costs to doing this. There's more time perhaps early on to stand up a more digital approach, a more model-centric and data-centric approach. There might be growing pains from the workforce perspective and making this work. So those do have real costs. So the goal of this work was to kind of show that the benefits outweighed the costs. There's a positive return on investment in this particular case. So the references are on the previous slide. You can go more into detail, but we summarize this as there was a $3 million investment, and they projected a almost $11 million return on that investment in this particular case. And that's particularly because even though there was initial this orange line here, initial MBSE startup investment, again, in the realm of $3 million. The savings over time, because we're able to identify errors much earlier, and they even projected even higher potential savings, upwards of $26 million in the errors that they weren't able to kind of detect and find. So over time, these errors, compound. The earlier we detect them, the lower the cost is to fix them, and that, quantified can give you an actual return on investment. You actually are improving your, program costs through this more model-centric, digital-centric approach. Okay, the final case study I have here, where are we at? Okay, final case study we have here is this capture and orient module for a potential Mars sample return mission. This is done by some work by some CSU students and faculty as well. So I wanted to highlight kind of this example. One key point that I want to bring away from here is how much information is actually in developing complex systems, and having all that information not connected, not automated, not linked, the digital thread concept can result in lots of burden to the engineers in maintaining that information and understanding the information, et cetera. So in this case, the MBSE approach, it was found that approximately 49% of the total knowledge processing was automated. Knowledge processing meaning, things like requirements or the results of simulations, those type of aspects that, do in one place, but they also are needed in other locations. Can we have that automated or have that linked in some way? So they found, looking through the elements for this particular, this is one module of a larger system, that there is almost 6,000 different kind of connections, knowledge connections that need to be understood. And in a non-MBC approach, it's argued that those are all done manually in some way. And an engineer is the one making those connections, understanding those connections, updating those connections, et cetera. But through an MBSE approach, we're not necessarily able to achieve all of them, but about half are now automated in some way. And that can greatly reduce, errors in the costs associated with maintaining this information. And perhaps in the future, that percentage increases even more, where the total knowledge of processing gets closer to that 100% goal. And humans are tasked with some other more important activities than simply maintaining the information in the system at that basic level. Okay, so some comments, tips, game changers, effective benefits, a bunch of kind of concepts here to kind of conclude this discussion. So what are some key game changers of digital engineering? Well, the still put forth that fundamental engineering principles prevail in this case. It's not redefining some of those core concepts that allow us to do effective system development. We are still doing good systems engineering, good engineering in general. They're just enhanced by technology, and we're able to, perhaps achieve those fundamental principles in a more effective manner. Another key aspect is the rapid digital evolution kind of idea. Processes are continuously evolving. Current technologies today maybe soon become outdated and replaced by faster, more efficient tools. The game changer of digital engineering is that you can actually incorporate more readily those rapidly evolving technologies. Unlocking data is key here, and that's part of that point I just made. Data capture and manipulation is essential and requires a digitally savvy engineer. But once you have that data, there's a lot of things you can do with it. A lot of advantages that can come from having data that was not accessible before, or just not even defined before. Collaborative practices reborn, collaborations in real time, co-design of multiple things, the better review processes, all that can be kind of, this is that culture side. We thought, can we do better reviews? Can we identify those errors earlier through those reviews? Is it easier to do reviews so we can have more of them or less of them, right? Depending on kind of the interpretation of the value that this digital, more model-centric approach might have for us. And then finally, improved optioneering. A lot of times, we're trying to decide on different options to make our systems, have the capabilities that we want them to have or meet other goals like cost versus performance benefits. Well, having a more digital approach, say also having things like digital twins defined, enable new and more efficient ways to generate multiple design options and evaluate them. We can do those explorations in a much more rapid way rather than say having to build things in the lab all the time, and that can be much more expensive in evaluating the potential solutions that we might be considering. Now, I mentioned this idea of bringing in new technologies, very rapidly changing technologies, and there's a variety of these type of things that can be kind of thought of as connected to or a part of the aims of digital engineering to achieve better collaboration, more efficient practices, etc. So let's go to the next bullet point here. So here's a summary of some key ones, big data analytics, VR, augmented reality, cloud computing, artificial intelligence, digital twins, digital manufacturing, more representative but potentially more expensive physical models, data visualization, and then there's still a question mark there of new emerging technologies. Right? All these aspects, I want to bring them into my development process. And often the question is how can I do that? Well, by having a more data-centric approach and having digital threads between them, you're able to perhaps better bring together these different technologies, less growing pains, and actually have them realize the benefits that are perhaps put forth by some of their kind of key proponents. Okay, so what does this mean? Well, there is, the potential for big changes here. So the traditional systems engineering V is still in use, but it might be more repetitive and shorter time frames. Thinking of things like rolling wave or agile kind of perspectives here. That increases flexibility, the ability to adapt the development processes to changing goals, changing needs. Also, just potentially do more effective development where we're not waiting so long to understand if something needs to be updated. Another major aspect here, hopefully pretty self-evident from the definitions and the aims that we've been putting forth, is that we'd be transitioning away from a more document-centric to more digital project artifacts or more model-centered artifacts. Another major aspect that might be seen here is less work creating things that are representations of our system and more automation of that process. We can take the data and we can take the models and get generation of reports, views, etc. from that information rather than manually creating it from perhaps an outdated or just a cumbersome and expensive approach. Also, we might have more sensor repositories and hopefully effectively enable digital threads through system development and retirement. That means as the system is continuously evolving, or even as it's retired, or as new programs are put forth that are similar to previous ones, I have that repository with that information and potentially ways to interact with that information with a very relatively low cost of entry. Then the culture side, changes in attitude and cultures within the established SE community. This is, title of this talk, transition, still in a transition phase, and it probably will be for a long time. But as more and more, those case studies come up, as tools get better, as the best practices learned both, as a community as well as specific organizations become more defined, the fundamental attitudes and culture may be shifting towards this more digitally data-centric, model-centric mindset. And finally, here, another key aspect to highlight is the idea of cybersecurity at all levels. When we make a more digital, approach to things, we need both the processes that there's a potential larger risk from the security perspective. So we want to build this into both the digital engineering practices we have, as well as more into our system solutions, so that they are more software centric or whatnot, that we are able to meet that particular challenge. Okay, so some expected benefits. One is informed decision making, greater insight through increased transparency. Again, that idea that we have information available to us. Enhanced communication, novel communication mechanisms in terms of the ability to ask questions and get their responses without having a human in the loop, or ask more complicated questions that one person might not have the answer to. Give me all of the things in this one area. That's something that would require a lot of effort perhaps in the past, but now I'm able to do that more effectively, as well as communicate to someone, either through the enabling technologies or through the data that's now available that wasn't available, what the system is and how it's performing, etc. Increased understanding for and greater flexibility, adaptability in the design. We've already talked about kind of the idea of being able to do more of a spiral development in system engineering versus a more monolithic top-down approach. We need more digital practices to really to promote that ability to be flexible and adaptable in the design. Fourth one here is increased confidence that the capability will perform as expected. The building digital threads so that we're able to do, say, verification earlier in the process, and we're able to have, the subject matter experts that can tell us early on whether or not something's going to work or not work. They have that information sooner rather than later. Will give us that increased confidence and perhaps lower costs for future testing, et cetera. Increased efficiency in the engineering and acquisition processes as well. One argument definitely to make here is, by creating the data, by creating the models, you're able to, use that and keep it and build future programs on the best practices of previous programs, on reusing the data from previous efforts that can greatly, over time reduce the system development times, give confidence to those who are purchasing or acquiring and validating our systems that they're going to work well because there's that evidence of previous success. So over time, expected benefits of having the whole community in a more digital engineering paradigm is general improvements in the acquisition and engineering practices.
Don't go too much
here, but I just want to highlight the idea that the discussion here sometimes is complicated because benefits are very much interrelated. So we're going to see in a second the direct benefits in green, the adoption factors in blue, and the resulting or secondary benefits in gray. And they're all very much interrelated. The idea that we get better reusability, but that really leads to reduction in time, which also leads to reduced waste. The idea that there's lots of benefits, they're all interrelated. So if we're really trying to understand the advantages that we're going to have from a digital engineering perspective, we need to have a little bit more nuanced, thought process of how these benefits are realized, how these benefits kind of work together to realize some larger scale things like reduction of waste or reducing costs or increasing efficiency. Like, what are the basic principles that yield those outcomes, as well as what are some of the factors that we can do in the blue boxes to improve the effectiveness of some of these kind of direct benefits that we're putting forth, like tool infrastructure, libraries, greater tool usage, training, knowledge, skill development, that type of stuff as well. Okay, so parting thoughts for you to have here is, keep up with the digital evolution. Digital engineers must keep up with the digital trends and make a habit to explore and learn about them. Organization must do so as well as, also promote their engineers to investigate these type of advances are being made so that they're able to understand, will it work? How can it work effectively for their organization? Another key aspect is learning to use the tools, implement the processes, and code more basically. As if you want to take advantage of the new data available, the mechanisms for interacting with it is not manual. It requires some understanding of the tools and the coding practices required to access it, that type of thing. So fluency is required to realize the benefits of digital engineering. So we do some of this at CSU, but there's lots of resources available as well to kind of understand specific enabling technologies, specific tools, et cetera, as a part of the digital engineering paradigm. Another aspect here is soft skills still matter. Not everyone understands the technical aspects or is going to be fluent in every tool or every code or every presentation of the information that you're trying to convey. So digital engineers still must bridge that gap through effective communication and collaboration. We must understand that even if some parts of the organization transition to a more digital paradigm, those approaches might need to be effectively still communicated with other groups until everyone's on the exact same page, perhaps, if that ever is possible. And then finally here, diverse skills and backgrounds are important. This is a pretty grand vision, right? We're trying to fundamentally change how very large organizations might be doing their development processes, and for that to work for everyone, the aim should be to get different kinds of expertise and specializations and backgrounds into a team to develop an effective enterprise level digital engineering approach. It supports better communication and collaboration. So what does that need to look like for the different teams, the different groups that are, it's intending for us to, build digital threads and communication linkages between. Okay, so I think I'm pretty good on time. So now I have some discussion questions. So, open it up for, more broad questions, but I do have 3 here for you to be thinking about if you want to give a particular answer to any one. Where do you see a particular need for digital engineering or digital transformation more broadly? The second one is, what specific challenges have you observed or do you foresee with adopting digital engineering practices? And then finally, do you have any digital engineering success stories you would like to share? So with that, thank you everyone for listening to me, ready to have a conversation about this topic.
Richard, Dan, you want to answer the question?
Yeah. Let's see. Okay, I'll go to Jose's question. So the question online right now is, I didn't mention modeling and simulation very much. How does this area fit into overall concepts you spoke of? So I kind of consider modeling and simulation as a part of those enabling technologies. So if we go back a bit, for example, I have the physics-based models as a part of these enabling technologies. So the ability to have, we already are doing modeling and simulation, right? We're already able to do that to a certain degree, but often that might be disassociated with other parts of the development process. That is the concept of digital twins. So I think a key aspect of the modeling and simulation paradigms is being able to bring those results closer to other domains. Both the other domains might define things that help us do a better job of our modeling and simulation, as well as we can better communicate the results of those modeling and simulation efforts back up to, say, requirements. We're able to use those results more directly, more rapidly to understand, is the system going to work as effectively as it might need to be. And if we think of the digital thread picture, for example, I think modeling and simulation is just a key aspect of integrating different tools that do the specific types, the best of breed concept for those modeling and simulations with the other pieces of our system that capture things like the software, general software side or the requirement side, et cetera. Let's see. So good questions coming online. So yeah, the question is, are there killer examples of digital engineering after the product is introduced into service? It's a good question. So all the examples I put forth here are either in the development side or, for example, the aircraft example I gave, the Boeing aircraft example, does have prototypes available. So just simply, again, having prototypes available in that very relatively short time frame, but also have capabilities that weren't available before, I think is a really strong example of again, this is relatively modern because these practices being applied to such large programs is still relatively novel. But I think this is a really, really good example. The other examples are still very much more in the kind of conceptual design phase of things. So another thing here for item 2, industries with strong regulation that impedes the ability for organizations to change the status quo for feeling to fail to convince regulatory bodies of the need to maintain or have some minimal level of quality when transitioning digital. One example would be medical devices and the FDA regulations and expectations of work products, still very document centric. So yeah, I definitely agree with that. The first slide that the first couple of slides that I had kind of on the DOE acquisition side, it's a slow process, but there is, I think, much more of a push. If you look at the DoD digital engineering strategy, there's a lot of kind of support from higher up to try to put forth these practices. So maybe other industries also need kind of some of that push, where the regulation side, the expectation side of what they deliver will need to be changed. So that could be one way you might be putting forth or pushing this idea is to impact that perspective and to show how it's bringing advantages to certain industries already. But also, I would argue, an effective digital engineering strategy meets the needs of the program at hand. If that program need is to meet, say, FDA medical device regulations, then how can we build a digital engineering strategy that makes it easier for us to produce those work products? The products still might be very document centric, but how we create them, how we develop them doesn't have to be. So I still think there's room to bring these practices in. Are they going to be reviewing a model or are they going to be reviewing the documents, right? A lot of guys, it's still going to be kind of more that document centric review, but how much work is needed to create that artifact essentially. Okay, so yeah, I can make these slides available. let me show you so yeah, Clarabelle, the link is here if you want to write that down quickly for this submarine warfare example here in particular. Are there questions in here? Yes, go ahead, Jeff.
Very wide on cases, but like for your particular case studies, how much do you now are involved in the process?
So yeah, I don't know if I have, on these specifically, but one of the enabling technologies is like cloud computing and things like that. And also just the fact that we're able to do more computing enables other technologies that might not have been feasible in the past. So the answer is a lot in many cases. The digital approach. Yeah, I think they often, if you're thinking that's on the scope of some of these large examples, enterprise buy-in from like the data infrastructure and computing infrastructure side, so that you can stand up the processes and tools that are needed to realize these visions. So yeah, that is, again, we talk about costs, right? There are sometimes costs here to developing these kind of systems in place. One of them certainly might be the computing aspects, but again, that might bring capabilities that you didn't have before as well.
Hey, Dan, this is Tim.
Oh, well, go ahead, Tim.
So just a comment to your first question. I was at a clean tech competition on Wednesday night, put on by an organization called Digital Wildcatters, which would imply disruption of digital stuff. It was in downtown Denver. And one of the companies was called Prolytics, and they were touting themselves as the only organization in energy services to do any kind of digital engineering work. I just tell you that as a way it's spilling over, I guess, in various industries. They mentioned the confluence of engineering and IT and data analytics, and their process was to build digital twins. And they were promoting this idea as being a new science called engineering technology, I guess you would call it, engineering technicians is what they were promoting themselves as. And I just thought that was interesting that they were kind of rethinking this whole idea. Systems engineering was not mentioned anywhere in this discussion, but it's just a spillover of a variety of ideas into a different set of industries where the same things are being accomplished.
Yeah, that's definitely really interesting. A lot of the motivation here is coming, from some of those defense programs, but I think they identified those needs earlier, at least, certain programs because of their scale and complexity. But as other domains like energy systems, other transportation systems, whatever, they become more complex, they're probably going to start hitting that same barrier where they start identifying the need for, digital engineering technologies or whatever you call it more broadly. So again, lots of different industries I think are behind in some ways than others, but also they're not maybe at quite the point where some of the values would be as large a scale as a submarine program or something like that. But yeah, thanks for that comment. But
Yeah, so I guess I'm kind of struggling with when is the correct point to implement, these MBSE approaches versus, like at $3 million, you have to invest that much to consider relevant, or kind of when and where the implementation tools.
Yeah, so it's a really good question. For example, if you didn't start from day one on using these approaches, are you still going to be successful if you transition to it? I think the earlier you do it, the better, because you are able to realize the benefits and over a longer period of time. But I also don't think that there's the inability to transition. So in this particular example, you can see the gray graphic is when they specifically did, my understanding of this was the full transition to this space versus I think early on it was, some small subset was understanding and perhaps maybe doing somewhat duplicate work to understand what should it be. But, once the transition has been done, you're able to kind of realize those benefits. So I don't know if I have a good answer, kind of like what scale of system, for example, would give you where MBSE is strictly required. I often think about it in terms of complexity, and that can come from a lot of ways: the systems complexity, the development complexity, the technological complexity. anything that's kind of more in the direction of more complex, then these approaches at least are reducing the risk of during the system development process, rather than you realize a failure too late that may have been corrected because someone had the right information at the right time, for example, or there wasn't a misunderstanding or miscommunication, or you simply just the cost overrun because people were doing the same thing and they weren't working together, that type of idea. So yeah, I don't have like a formula, but I think that's, I don't know if there's going to be a formula, but I think that's kind of an idea, right? It's like, I think especially take a look at kind of this paper of understanding what the, potential costs are for standing up some of these efforts. And you can do, especially if it's an organization or some effort that you have some historical data on, like, did I fail at some point and how much did that cost me? That can give you a lot of insight. That's what they're doing here, essentially. That gives you a lot of insights into, should I do this or not? And will give me the return on investment that I might want, or, ROI is not everything. There could be other benefits that are brought in terms of like stakeholder communication with, and again, delivering something on time can have a lot of value, whether or not it's on cost or not, that type of kind of perspective as well. So hopefully that's a reasonably satisfactory answer, but yeah, I mean, again, it's a transition here, right? It's not I'm not saying, this is an established method that you can go and just press a button and it does your design for you.
How scalable is this? Like, if you're like a small company doing like control systems or something like that. Like, would it be worth transitioning this, and would it be in a time?
Yeah, so you can definitely, there's a lot of research on doing this on smaller things, right? Versus just these really big things. The benefits, sometimes are hard to quantify, but the ability to perhaps capture and do the system engineering activities or engineering activities more generally that you want to do, and have the value that's brought later in the process can be done at any scale, is what I would say. There's also just like the ability to better communicate and all that any size organization I think would benefit from it. But if the training costs and the startup costs are too high, then that's where the ROI maybe argument comes into play, where too small. I think sometimes the question is more like, do you need like systems engineering? Sometimes if you need systems engineering, should you be doing it with a model-based system engineering approach, or should you be doing it in a more traditional whatever your current processes are? Maybe I do have a backup slide that maybe is aligned with this. This is a NASA graphic in terms of time spent on systems engineering versus the cost overruns of the program. And if we see the scale on the y-axis is 0 to 200% overrun, the scale on the other axis is 0 to 25% systems engineering. And there's a general trend that the more systems engineering you do, and the reason I put this in because I might make the argument like maybe in the future there'll be something like this for more broadly digital engineering, not just the idea of system engineering, where you have a more digital engineering centric, maybe it's like that knowledge management side of things, where more of the system development is managed through digital threads and digital means. Your cost overruns might be lower on certain programs, things like that. So, the answer to the question, I think it does bring value, and maybe it's it's not picking every possible enabling technology and bringing it into a small company that does control systems, but rather it is bringing what is identified as the key target technologies together that might not have been brought together through these mechanisms, right? I think like digital threads, a mechanism that you could do between two tools, right? Does your organization have a need to connect those things together? That's what I would be asking. Could be just one digital thread really enables you to do more or do things more efficiently. Yeah.
Do you think more integration of digital engineering do you think it's well adapted to barriers of confidentiality levels between, like, say, civilian and defense, or between different companies in terms of IP? Or do you think that's potentially an issue that needs to be involved?
Yeah. So the question is kind of on data-centric things and model-centric things. The potential for security issues or IP issues as well, right? So that's part of, I think, a good digital engineering strategy is the ability to protect your information. A lot of these tools do support, for example, like the MBSC tool supports classification levels for information in it. So you can specify that certain information is only, available to certain, users of the system. Similar things, doing, an effective data repository that has, role-based access control is required, right? Standing up this approach with these factors in play, I think, is important. What I would say is that a good digital engineering strategy allows you to share more information with those who have the ability or should see it, right? Maybe it does introduce some potential for sharing information for those who shouldn't see it. And that's why I said, cybersecurity at the beginnings, to make sure you're, if you're putting everything in an enterprise cloud, does that introduce you to risk? Probably. So you want to consider those factors. So yeah, again, it's definitely something that the tools are thinking about, and maybe you are, you can put a computer in a room with no internet connections, and right, is that enough to do your engineering, or do you need that to be connected to your network, right? Or do you need the data to be connected to the network? So I think it's understanding, is that capability worth potentially some of that risk? Yeah. All right, I think, let me see. Sorry, I haven't been keeping up. Yep, thanks, Tim, for the references. That's a good question. I won't claim to have any insight. Would this curve look the same today? I think these are all very old. It's like 2000, maybe it's like two decades old now, if I remember right, when this was put out. So I'm not sure if, there's more data points that can be put in here that would give better insight into current trends, or, maybe we start coloring dots of traditional system engineering versus, model-based or more digital engineering centric things. Good question. But I'm not aware of an updated graphic. At least I haven't seen one at this point. But, again, this is kind of, the trend is kind of like do more upfront engineering or more, systems focused thinking, does that yield, fewer problems down the line, which usually are why there's cost overruns, essentially. Let's see what time we're at. Maybe I'll ask the final question and then we'll wrap up. What are some of the ethical considerations associated with the use of digital engineering? Interesting question. I'm not sure. Yeah, I think of it a little bit as if you're doing, a lot of times you're redefining how you're doing traditional practices. There could always be, data privacy concerns or things like that, bringing in that data into the enterprise to make better decisions, right? There's obviously potentially some ethical questions of using that data more effectively. And that's sometimes how organizations are perhaps tailoring their products to meet specific user needs. So maybe kind of that like personal data perspective might be something to be thinking about in the context of digital engineering. Yeah, I don't know if I have a better answer at this time for kind of that. That's definitely an interesting question to think about is, does this, are these novel mechanisms and capabilities, potentially things we should be considering as, features that we want to do beyond just the, say, return on investment perspective. Okay, maybe with that, since I think we're a little over time, we'll wrap up. But yeah, feel free to reach out to me or Ann if you have follow-up questions. Maybe I'll go back to the first slide. Our emails are there, I must close it. Thank you everyone for attending the talk, and yeah.